This is a pre-lab for Lab 3 of ENP231. And in class leading up to this lab, you will have been introduced or be introduced to nonlinear devices. So this follows after having learned about linear resistors. And as a way of introduction to nonlinear devices, we're going to study or have a lab on LEDs, which are light-emitting diodes. They're part of a larger class of devices called diodes, which have a very nonlinear voltage current relationship. And so this is our way of giving you an introduction to a nonlinear device. And we thought we would design it around creating a useful little LED fob, something you can hold in your hand, you press the button, and it's like a little flashlight, essentially. So kind of as a little bonus in this lab, we're providing a little circuit board that you will be able to solder up and take home with you. This actual circuit board assembly won't happen during the lab. It's kind of just something on the side that you're free to do. The components are there for you to take and to keep. So, but the work that you do in the lab will help you appreciate and understand how one might design a more practical LED fob. So what I want to do in this pre-lab is just to give you a kind of a tour of the instructions that are going to be provided for this lab, and in doing so give you a sense of how the instructions are laid out, how you would use them to work through the activities in the lab, and then in the subsequent write-up and work that you'll do leading up to submitting your lab report. And I'll have probably a separate video that will go into some of the theory or concepts you might need to understand in order to be able to complete this lab. Okay, so what you see before you here is the top of the Lab 3 instructions. There's an outline here, and there are 10 sections. Okay, this looks busy, but we've worked hard at laying this out in a way that makes it very efficient to use once you understand the layout. Okay, this layout will be adopted for multiple labs throughout the semester, so hopefully over time you'll start seeing a familiarity. And these are the basic elements. You'll be given objectives for the lab. So why are we doing this? What's the point? You will be given a summary statement that basically gives you kind of a narrative of this is what you're going to do in the lab. You'll actually be given a list of supplies that come from your kit. So your class lab kit that is yours to keep. There are components, say some resistors or LED, that's in your kit. And if there are any supplies that you need for a particular lab, those will be listed there in section 3, the kit supplied components and breadboarding supplies. 4 is lab receivables. So these are things you need in order to complete your lab. So if there are additional components, special components that aren't in your kit, we will provide those. Clearly, any lab equipment that you need will be listed here. So you have power supply or multimeter, etc. Section 5 is the lab deliverables. So this is kind of skipping to the end of the whole lab session and then the subsequent work write-up report that you'll generate. And at the end, there is a deliverable. That means that these are the things that you are going to deliver back to the instructor after having completed the lab. You won't complete all of these within your 3-hour lab section or session, right? A number of these will be completed outside of lab and will be bundled together in ultimately a PDF, electronic PDF that you will submit as your lab report. So that's a good place to go if you want to kind of look to the end and say, okay, where's this all heading to? What's in the end? What do I have to deliver? It certainly will be an area that you'll spend a lot of give a lot of attention to when you're writing your report and making sure that you have everything you need before you submit it. Okay, section 6, 7, 8, 9, and 10 are the sections that you're really going to focus on when you carry out the lab. Okay, so actually let me jump to section 9. I'll come back to 6, 7, and 8. Section 9 is basically the lab procedure. Okay, it tells you do this, then do this, then do this, then do this. And it's given at a very high level, so there may only be a couple things listed. And it's brief. It's not enough information for you to know exactly what to do, but it gives you a good sense of like the main salient tasks that you're going to have to do in your lab, okay, in the lab 3-hour lab session. Section 10 then is kind of a checkoff list. Before you leave lab, these are the things you should have accomplished in lab. All right. There's more things you're going to do after you leave lab. Those will be captured in the deliverable section, right? Things that you're going to, like some analysis, or it's some things you're going to do electronically ultimately that in lab you're going to do on paper. Okay, so when you go to the lab procedure details and it tells you measure the LED voltage current characteristic, it's not going to tell you how to do that. Okay, so in order to know how to do that, you're going to look at section 7, which is a lab setup and testing detail section. There should be a section or subsection that is titled something to the effect of LED diode VI characterization setup, and it'll show you or tell you how to set up the experiment and what you should collect. All right, and specifically, maybe it'll give you, tabulate this data or whatever. Okay, so you're going to want to refer to the setup section to know how to carry out some procedure, some testing procedure that's listed in the procedure section. Furthermore, in the procedure section, when it says collect diode VI data, you not only need to know how to set up that experiment, but okay, well, how much data do I take? Over what current or voltage range? So there's some specifics. There's a specification in terms of like data points, and how many data points, what's the starting current, what's the ending current, okay? That information is going to be found in section 6, the lab relevant specifications, okay? So I've mentioned so far section 6 and 7, the testing detail or the setup detail, and then the specification detail, and those are needed, or you'll reference those when you try to carry out one of the lab procedures, such as collect diode VI data. Okay. Sometimes you're actually asked to do some analysis. Once you have data, figure something out with that data. So that's section 8, where there might be some relevant subsection that says, here's how you do such and such analysis. Okay, rather than bundling all those details from section 6, 7, 8 within the lab procedure, which just make that lab procedure really long, we've pulled those out and stuck those in their own relevant sections. Now, another use of section 6, the specification section, is when you are tasked to actually design something in a lab, that section will have that. Okay, and we'll look at that section in a minute here. In this case, you're ultimately going to design, quote unquote, an LED fob, which really consists of mostly of just selecting 2 resistor values. Okay, well, how do you know that you've picked the right resistor values? Well, you pick the right resistor. You pick the resistor values such that the LED fob that you designed behaves according to what has been specified in the specification section. So I will show you that here in a minute. Okay, so that's a quick overview of these 10 sections. All right, and I won't normally go through all that, but since this is the first time I think that these 10 sections are used, I thought it would be useful to tell you about them. Okay, so some objectives for this lab. You're going to be dealing with a battery. You're going to be dealing with an LED. So one of the objectives is to learn how to make a simple model of a battery, basically by modeling it as an ideal voltage source and a series resistor. Okay, you're actually going to measure physical voltage and current of the battery, take a couple data points, and then you're going to fit that, or fit a voltage source plus resistance model to that data. Okay. Second, to learn and practice characterizing the DC behavior of an LED. So you're going to apply a current or voltage to the LED, measure the voltage or current, collect that, put it in a table, plot it. You're going to learn and practice to use Excel to capture, analyze, and present lab data. By the way, that you're going to do in your write-up portion. You will not use Excel in the lab. during the 3-hour time. We want you to do it by hand. Fourth, to learn and practice using a load line to solve graphically a circuit involving a nonlinear element. So that you will be doing in lab. So whenever you have a nonlinear element, things get complicated, get nasty, if you will, in terms of the equations, all right? Well, one way of avoiding having to solve nasty nonlinear equations is that you can actually solve or estimate. It's really an approximation. You can find an approximate solution by doing a graphical analysis, and that's what we're going to do in the lab, okay? We'll learn other ways of solving nonlinear circuits in class, but in the lab, we're going to just use a graphical method. Okay, now there are going to be some objectives related to homework that goes along with this lab. So it won't be a lab, it'll be a homework assignment, but these are some other objectives which deal with learning to use the Shockley equation to model the voltage current characteristics of a diode, to actually extract the model parameters, Shockley model parameters, from diode data. Okay, so you will have diode data from your lab. In your homework, you're actually going to be asked to actually use that data. Okay, or I'll give you a standard data set so that everyone uses the same set of data. And then learn and practice modeling a diode in SPICE, our circuit simulation software. All right, so just an FYI that what you're doing in lab is actually going to be put to use in an accompanying homework assignment, and hopefully all that together will help you have greater success in learning the concepts that are related to, in this case, studying nonlinear devices. Okay, I'm going to skip the summary because it's going to come out as we talk through this. All right, I'm going to skip the kit. You can look at that and see the parts that are come from your kit that you will be provided. Lab receivables, these are things that you're going to need to be given. So there's an extra battery holder that won't be in your kit. There's testing supplies, so power supply, handheld multimeter, and a bench multimeter, some adapters or cables that go along with that. Okay, that'll help guide you in knowing when you get to lab what equipment, what cables are you going to be using, etc. All right, lab deliverables. So I'm gonna fly through this because I don't want to. Clearly, you need to read through this in detail on your own. I just want to show you kind of a higher level overview of the entire document here, okay, and then focus on the procedure. But deliverables, thing I want to point out here is number one always is going to be standard lab report deliverables. There's a separate document that applies to all lab reports that you need to read and study and comply with on every lab report, okay? And so that's not even, those things are not even going to be repeated in individual labs because it's a given that you're going to be following those, right? So basically in your lab deliverable, so this is a PDF report that you will submit electronically. You also submit a hand copy, hard copy, unless instructed otherwise. Is one, or point two here, is basically VI data, voltage current data, from a white LED that you will be characterizing. It'll be tabulated, it'll be plotted. Two, a little coin battery, a CR2032 battery. You're going to have voltage current data for it. It's going to be tabulated. It's going to be plotted. All right. You are then going to have a battery model, which I told you already is a voltage source in series with the battery. You will have a section that will basically say, hey, here's the data that I collected for the battery. Here is the ideal, here's my model, which is basically just a voltage source with a resistance, and you will actually give the voltage source a value, you will give the resistance a value, and you will show in this section, basically you'll back your model, like how did you get to it? You did some analysis. In this case, it's a graphical analysis, drawing a line over your battery data, getting the slope, getting the y-intercept, and coming up with the battery voltage source value and a resistance. Okay, so that's section 4 here. Section 5 then is actually the design of your LED fob, which has two parts. Essentially, one is you are required to design an LED fob that actually operates the battery, the LED, at a certain current. There's actually two current levels, kind of like a dim and a bright level, and you're going to present the analysis, if you will, the work that you did that led to the two resistance values that will actually result in the LED operating at the desired current, okay? And then secondly, there's a requirement in this LED fob design that there's a certain functionality. There will be two, excuse me, two little tactile or momentary switches, and depending on which one you press, and if you press both of them or neither of them, it'll either go dim, off, or bright, and you need to implement a little circuit that will do that. So you have to kind of think through what's the circuit that's going to accomplish this. We don't provide you that detail, but we do tell you precisely, how many components will be in your circuit. So it's kind of a constrained design problem, if you will. Okay, there's a little extra credit problem there that you can provide in your write-up, and that is, don't you wonder if you power an LED with a little coin cell and you design it with a resistor in series with your LED such that the current is limited to some amount of current, how long will the battery last? Okay, so this extra credit problem probes on that, and it gives you a link to an actual data sheet for a CR2032 coin battery and asks you, can you estimate the runtime? How long would the LED last? Okay, so now section 6 is the lab relevant specification. So as I told you before, this is a very concisely stated quantitative requirements for the lab, and it could either be quantitative specifications related to some test you have to run or to some design activity. In this case, it's both. So 1 and 2 here are the specifics to collecting LED data and then battery data. So just as an example, the first one, it says collect VI data for the LED in a 1-2-5 sequence beginning at a current less than 1 microamp and going up to about 50 microamps. Actually, that'll probably be 30 microamps in your final version of these instructions. Okay, so what does that mean? If you start at 1 microamp, then it'd be 1 microamp, 2 microamp, 5 microamp, 10 microamp, 20 microamp, 50 microamp, 100 microamp, 200 microamp, and so on. Okay, so that's if you just needed a place to go to say, okay, I forget how many data points were we supposed to take, what's the range, you go right here. Okay, same with the battery. You're going to collect VI data, and you're going to collect the VI data for the battery by actually loading the battery with the resistor, and I actually give you the resistor values, and you're going to measure the voltage across that resistance from which you can calculate the current, right? So there's some details there. Note that there is more information about how you actually carry out these tests. That's in section 7, lab setup, down below, that you see at the bottom of the page, and I'll tell you about that next. Let's go to section 3 of the specification, though, because this is where the LED fob is specified. Okay, so these are the requirements. We've written this up in a way that kind of hints at what you would expect or become familiar with as a design engineer. Out in industry, when you go design something, you're going to have a specification. You could be designing an LED fob. It would have a number of specifications. A lot of them could be mechanical, it could be environmental, like for instance, the thing can be dropped in water, whatever. But here we just have some electrical specifications. We're just trying to get you familiar with this idea that in engineering practice, where you're designing things, there's always a specification against which your design is driven, essentially. Okay, so the battery source is 2 series connected batteries, these CR2032s. The LED is a 5mm white Piranha LED, which will provide you actuation, 2 tactile push button switches, denoted S1 and 2. The LED should have 2 brightnesses called bright and dim. And in the bright mode, the current should be about 6.8 milliamps. And in the dim mode, it should be about 0.5 milliamp. Okay, about. This is an approximate design. You're not going to nail it exactly. You just try to get close to it. Functionality. How does this thing work? If you press S1, it turns on the dim mode. If you press S1 and S2, it turns on the bright mode. If you press S2 alone, it does nothing. And obviously, if neither switches are pressed, then the LED does not turn on. All right. And finally, bill of materials, or BOM. What are the constraints? So here's a little. Since we don't give you the final circuit, you might be wondering, okay, how many resistors do I need? How complicated does this circuit have to be? Well, here we tell you precisely what's going to be in your circuit. You're obviously going to have 2 batteries. We give you plus battery holders so you can snap the batteries in and out. You only need 2 resistors, and you need 2 push button switches, and you need 1 LED. Okay, so in the end, your final design for this LED fob is going to be a schematic, a circuit that you're going to draw up that's going to show how these, let's see, 2, 4, 6, well, it's 2 batteries, 2 resistors, 2 switches, and an LED. So that's 7 components, how these 7 components are wired up. Right? And you're going to have values for R1 and R2. Okay? Those are the things that are not known. How do you wire up these 7 components in a schematic? And 2, what are the values of R1 and R2 such that when you press S1 and S2 according to section 5 here of the specifications, you get the 6.8 milliamps or the 0.5 milliamps. Okay, so that is your design task. Now, section 7, I won't go through in all detail here. You're going to have to read through this, but we'll just kind of walk through at a high level just to highlight that there is some detail on here provided as to how you're going to set up your experiment. So there's a section 7.1 called LED IV characterization setup. So when you're asked in the procedure to collect IV data for the LED, this is where you go to see the setup. All right, so I tell you, you got a power supply here. You have this BNC1201 bench meter in series. You also have another resistor here, which, by the way, it says 10 ohms, but I say, but you're going to use 100 ohms in this particular setup because this drawing was created originally for testing a different device, not this particular LED. And then you have a handheld multimeter that is going to be measuring the DC voltage. Okay, so again, you're trying to collect VI data, so you need a way to measure voltage and current. This meter measures voltage across DUT's device under test, basically the LED in this case. This is the current that flows through the LED. So those are your 2 instruments that are going to be measuring voltage and current. Your power supply has an arrow through it because you're able to actually control the voltage so as to get the current flowing that you desire. So if you say, hey, I want to be able to test this now at 10 milliamps, then you're going to adjust the power supply until you get 10 milliamps. All right. By the way, when you're measuring really small currents like a microamp, you're welcome to switch out this resistor from being 100 ohm to something much larger. It'll help you actually have better control, fine control of the current flowing through the circuit. Okay, otherwise you might find that you just can't, when you get down to that low of current, you just can't dial it in as you want just by turning the power supply voltage knob. This is what it might look like physically when you wire it up. Here I show a bulb, but you're putting an LED here instead of a bulb, but this is what it might look like on your bench, okay? When you collect your battery data, I don't have any pictures, but I have some narrative here that gives you some instructions on how you're going to actually measure your battery data, all right? And then, since this section is called lab setup and testing detail, and yeah, so there's actually, I thought there was testing. Sorry. What did I say? Setup and testing detail. So, right. So in section 7.3 here, there's some information on actually validating your LED design. So at the very end, after you've selected the resistor values that get you the 6.8 and half milliamp of current, you then need to actually build the circuit and test, is it actually doing what we're anticipating it to do? All right, so here is some testing detail. It's not so much telling you how to set it up, although I may have some information on that. It's more, how do you actually validate it? What should you do to validate this? All right, and there's 2 real validation steps. One is, okay, are you getting the 0.5 amps and the 6.8 milliamps when you run the LED with the resistor values you picked? And the other one is the functionality. When you press S1, S2, or both S1 and S2, is it functioning as anticipated? So I have some instructions on that. Okay, so let me skip section 8 here and go to 9, and then maybe I'll come back to 8 if it makes sense. So 9 is the lab procedure detail. So this is really, you walk in the lab, this is what you're going to do, okay? So I'm going to focus in on here now so you're clear on what you're going to need to do in lab. First of all, for this lab, all of your lab work, including all data collection, tabulating, and plotting, must be done by hand in your lab book, okay? That means, yes, you will need to do scaled plots. When you take data points, you need to actually mark off using the grid on your notebook to be able to make a nice scaled plot. Otherwise, you're not going to be able to succeed in your LED fob design because, after all, I told you that this nonlinear circuit is going to be designed using a graphical method. So you need to have a well scaled plot on which to do your graphical design. Okay, so don't use the computer to do this. Later in your lab write-up, you're going to transfer your data to Excel, including plots, and you'll use Word or equivalent to actually create your report. Okay, so 6 things in your lab procedure. 1, collect LED IV data. 2, collect battery data. 3, create a voltage source plus resistance model of the battery. So that's using that data. 4, design an LED fob by selecting appropriate resistance values. That's so you get your 6.8 milliamps and your 0.5 milliamps roughly. 5, validate your LED fob design. So now you actually build it with those resistor values, or as close as you can reasonably get to those values, and you measure the current. See, does it actually perform as anticipated? And then 6, clean up your lab station. All right, so that's what you need to do during the lab session. All right, and what I say right above that list of 6 things is, for additional details on completing each procedural step, refer to the relevant subsections of the following sections, things that we've already talked about. 6 is the lab relevant specification, 7 is the lab setup detail, and 8, which we didn't look at yet, is the lab analysis details. So the lab analysis details will be useful when, for instance, you are asked to create a voltage source plus resistance model of your battery, right? Step 3 there. How do you do that? You've got your data. How do you go about doing that? Well, the lab analysis detail gives you some information on that. Similarly, when in step 4 where it says design an LED fob by selecting appropriate resistance values, how do you select the appropriate resistance values? Well, you're going to do that by actually following some analysis details that are provided in section 8. So let me just make sure I do have those in there. So under lab analysis details, 8.1 battery modeling, 8.2 LED fob design. All right. Yep, and then lastly, 10 is the checkoff list. So before you leave lab, you should have LED VI data tabulated and plotted in your lab notebook. You should have the battery data, VI data tabulated and plotted in your notebook. You should have determined a battery model. You should have LED fob current limiting resistance determined. That's part of your design, right? Finding those two resistance values that give you the 6.8 milliamps and the 0.5 milliamps. And lastly, actual LED fob operating current. So you actually built the circuit, you tested it, you validated that it actually operates. Okay. So I know that was long this time. Hopefully in future pre-labs, we won't have to go through so much detail because you will be familiar with the structure.